And it's one question on the exam. So types of forces. Actually, let's take a quick step back before we get into the types of forces. How many people watched the video? Oh, it's not horrible. Well, not as horrible as I thought it was going to be. Okay. So what we're concerned about with our forces is how any two particles interact. So the video kind of goes through a little bit more detail on this. Chemistry is atom 1, atom 2. It's even simpler than that. It's proton 1, electron 2. What happens when proton gets near electron? Why proton gets near an electron? They don't repel. They attract. And we have hydrogen. Proton and electron. I have hydrogen. Cool, I have the first element on the periodic table. What happens if instead of having just one proton, I had two protons? What happens? Not quite. I bring two protons near each other and we form helium. If that was the case, then the mass for helium should be 2. What is the mass for helium? 4. So I bring proton near proton, what happens? They repel. Similar charges repel. Dissimilar charges? Sure. Different charges attract. Opposites. There's the word. Opposites attract. Okay? So how do we get larger elements beyond hydrogen then? Okay, I can't just add two protons, because if I add two protons, they push away from each other. We could try and add an electron, okay, but does the electron hang out with the protons? No, the electron hung out outside the protons. Our protons were in a nucleus, our electrons were outside. Okay? So how do I get the protons? How do I get larger molecules or larger atoms? I add neutrons. Okay? Neutrons come in as a little bit of glue and grab those protons and hold on to them and keep them all together in one little tight little nucleus. And then we've got our electrons floating around on the outside. Okay? Why do I want two electrons floating on the outside? To neutralize the charge of that positive. Okay? So I could build all of my atoms. Okay? Well, those atoms are going to start to balance their protons and electrons in slightly different fashions. That's where we had orbitals, okay, in our electron configurations. But what happens, say, if I bring two of those atoms and there are different weird balances of protons and electrons now near each other? Well, now the electrons on one atom will see the nucleus of the other atom and say, that's actually kind of cool, I'm going to go over there. Okay. Which then means I'm now sharing electrons between atoms. I now have a strong interaction. If I'm sharing, I then have a bond. Okay. But what if we don't actually share? We just say, that looks kind of cool, I'm just going to drift that direction, but I'm not going to get close enough to share. Is there still a force there? Yeah, I'm still drifting that direction. I want to be able to describe that force. I want to be able to describe the force when I'm sharing things. Okay? So we're looking at the relationships between any two particles and saying, what is it? Defining it. Okay? Once we've defined it, then we try to quantify it. And that's what everybody gets bogged down in when we look at general chemistry, is we look at all the quantification aspects and we stop looking at the qualitative. Hey, that's just cool. I'm going to go hang out there. Okay? That's intermolecular forces. Okay? We've already talked about a force between two particles. What was that force that we've talked about? Say that again? Interesting. We actually mentioned hydrogen bonding. Hydrogen bonding, I would argue, is an intermolecular force. That's kind of the new content. There's actually something that's a stronger attractive force that isn't hydrogen bonding. Okay, so we wrote that out, hydrogen bonding. I said, well, there's a stronger force than hydrogen bonding that isn't hydrogen, and isn't really ing. Bonds. Okay? Do I have different bonds? What type of bonds do I have? I had ionic and I had covalent bonds. Okay? So that was the first subcategory. Okay? When we looked at our bonds. We're looking at how those two atoms are now sharing their electrons. In the case of an ionic bond, we actually say they aren't sharing electrons. They've transferred electrons entirely across. That's why ionic floats in this weird gray area. Okay? How do we know it was an ionic bond? This was a metal and a nonmetal. Okay? Are all ionic bonds metals and nonmetals? No, but all metal-nonmetal bonds are ionic. Okay? So we have other cases that we have ionic bonds that aren't metals and nonmetals, but this gets us pretty darn close. How do we know we have a covalent bond? Okay, we could have nonmetal and nonmetal. And that was our initial definition. What was the issue that we talked about when we talked about bonding? We said something about nonpolar and polar covalent bonding, not just covalent bonding. Okay? Because what we were getting at is that if I take a look at the compound, say, HCl versus H2O, well, what's the difference between those? Okay? We could say oxygen's different between it. Are they ionic? No, they're covalent because they're non-metal, right? Okay? So if they have the same kind of bond, shouldn't they have the same kind of chemistry? Well, it makes sense. They have the same type of strength holding them together. We would expect them to interact the same with the rest of their environment. And yet, if we look at the name for those, and just to be officially correct, if we look at the name for those, HClHQ is known as hydrochloric acid, and H2O is known as water. Well, there's nothing really all that important in a name, except that if I splashed hydrochloric acid in my face versus water, I'm going to get a slightly different reaction. Okay? Why am I getting a slightly different reaction? Okay? And by slightly, that's an exaggeration. One, my face melts and I scream in pain, and one, I just get clean. Okay, what's that difference? They're both covalent. That covalent bond has to subcategorize out into nonpolar covalent and polar covalent. So instead of looking at just two types of classifications for bonds, we have three types. Which is why we can't use the nonmetal moniker anymore, because the nonmetal moniker doesn't work well. Okay? What do we use instead? How do we know we have a polar covalent bond versus a nonpolar covalent bond? We could look for a dipole. Okay, by show of hands, how many people know what a dipole is? Let's not use that definition. Okay. For those of you at home, nobody raised their hand. Well, one person raised their hand. Okay. So we can't mention dipoles. Dipoles are not going to help us here. How can we tell the difference between polar covalent and nonpolar covalent? Polar covalent does have oxygen in it. That is a possibility. But HCl is a polar covalent bond that does not have oxygen in it. So I don't accept that either. The difference in electronegativity. I like that. Okay? That's getting somewhere because that's officially how we differentiate. Okay? So, of course, as we come up with suggestions, we then need to test that suggestion. How many of you know the electronegativity for any element on the periodic table? No hands again. Really? Okay, 2 people. No, what element do you know the electronegativity of?
Depends. Can't you look at the top row?
Nope. Nope. Top row doesn't tell you electronegativity.
No, it's just the
You don't know.
It's just the
Okay, you know general trends. Okay, that can help out. Okay, but the general trends aren't going to be all that useful if we can't quantify it, and you're saying that we tell the difference by quantifying it. So I like electronegativity, but we haven't memorized our electronegativities, so that still doesn't work. And for those of you that didn't watch the video, that's okay. We already defined what these things were earlier in the semester. As a hint, the nonpolar covalent.
Polar is anything
Okay, so we're moving ahead here, though unfortunately it's not going to be the greatest move forward, but it is a move forward. Our polar covalent is everything else. Yes, that is exactly what I told you to memorize. The polar covalent is everything else that is not an ionic bond and that is not a nonpolar covalent. If you don't know what a nonpolar covalent bond is, you can't tell me what a polar covalent bond is, though. So we've got a step, but we need the other step. You're going to say it? A nonpolar covalent bond is looking at an equal sharing of electrons. So the difference in electronegativity is 0. The only time it is 0 is when it's the same element bound to the same element. Did I spell that right? Okay, so cool, that works for 1. That definition works really, really well. It is our strictest definition of nonpolar covalent. It's unfortunately so strict that we expand it ever so slightly. We expand it ever so slightly primarily for organic chemistry, which is a hint. Hydrogen, ow, and carbon. If I have a hydrogen bound to a carbon, that is by definition nonpolar covalent. So what is polar covalent? Anything other than those definitions. Okay? We have to be able to look at a compound and come up with that definition. Okay, Ying, sorry. Two, same. Is that the part you were complaining about?
Sort of.
Dang it. Okay.
I just don't know. I don't understand.
Same element to same element?
Oh, same to same. I saw this. Okay, now it's good.
Now you got it? Okay.
I saw same to other side.
Yeah, I don't know. All right. So when we look at anything in chemistry, what we need to be doing is looking at our bonds and saying, what type of bond is that? Because once I know that type of bond, I can then classify it according to that bond's strength, and that gives me information about how that molecule will interact with the rest of the world. Okay? And that's largely what I'm concerned about. I take molecules and I interact them with something else. If I want to know that interaction, I have to know what's causing it, and that comes back to the bonds. Okay? So we have to have these 3 definitions nailed down. And I totally thought there was a different summary slide in there, so we're just going to wing that part too. Okay? This is primarily to help those that missed the video. So what are we talking about in that interaction? I take a look, for those of you who watched the video, I didn't talk about CO, right? Is that the one I left off? Okay. So I take a look at the CO bond. Okay, what type of bond is that? It's polar covalent. It's not ionic because carbon and oxygen are nonmetals. They're nonmetals because upper right-hand side of that little staircase. Okay, that makes them nonmetals. Carbon and oxygen are not the same element, and oxygen is certainly not hydrogen. That makes that bond polar covalent. Okay? What I'm concerned about now is how this bond interacts with the rest of the world. Okay? So I bring in another bond, and I want to say, how do you interact? Okay? To simplify, the first thing I'm going to do is say, how would you interact with another bond just like you? Okay? Well, there's really only 2-ish ways to look at it, and we'll try and keep it in a linear fashion. Okay? I could have these interact. Let's just stick with that O then. Where that oxygen interacts with another carbon, or that oxygen interacts with another oxygen. Right? 2 ways. That's it. Make sense? Which of those interactions do I think is going to be the most prevalent? Oh, that's fun. We got top and bottom coming out of that. How do we decide? Well, this goes back to identifying what kind of bond we have. Okay, polar covalent. That means the electrons in that bond are being unequally shared. They're spending some of their time on one end of the molecule than the other. they're going to spend their time on the more electronegative element in that bond. And as Hannah suggested, we know trends in electronegativity. Our trend is that fluorine is the most electronegative, and cesium in the lower left is our least electronegative. So the closer we are to fluorine, the more electronegative we are. The more we're pulling electrons towards that atom. Okay, so the two atoms we're looking at here are carbon and oxygen. Which is closer to fluorine? Oxygen, which means what is oxygen doing to the electrons in that bond? It's pulling them towards it. By accepting those electrons, that oxygen is now gaining an electron. What charge was an electron? Negative. So if it's starting to gain an electron, it's starting to carry a negative charge. Okay, but it's not an ionic bond, so it can't be a formal negative. It has to be a partial negative. So we have the goofy little delta symbol. Where did it get that partial negative from, though? Well, by stealing electrons from the bond. Where do the electrons in the bond come from? From the other atom. So if oxygen is stealing electrons and becoming negative, what has to happen to the carbon? Has to becoming partially positive. Well, that's how that bond now sees itself, which means anytime I see that bond, I have that same charge generated. Which means when I now go through to look at those interactions, which of those interactions do I think to be the most favorable? The bottom or the top? The bottom should be the more favorable one because I'm now neutralizing that charge. You mean the exact same thing that allowed me to build atoms from the very beginning, protons being attracted to neutrons, or being electrons, to build an atom, is the exact same thing that's explaining how I'm building larger and larger structures? Yes. Yes, it is. That's awesome. It's the exact same principle all the way through. Okay? We aren't changing anything. We're keeping the exact same rules. Okay? That means this bottom interaction is our favored one. Okay? So what I should go through and do is now test this theory, this type of bond, because this was a polar covalent bond, and see what I would expect to happen if it was an ionic bond or a nonpolar covalent bond. And look at how all of those things then attract and stack with each other. In the video, I don't think I gave the answer, so let's go ahead and look at it. Let's look at a nonpolar covalent bond. Right? What is a nonpolar covalent bond? Hydrogen to carbon is the best example because that's organic chemistry. You could have given me same to same, but carbon to hydrogen is better. Right? We want the same idea as we did with the oxygen, so hydrogen to carbon, carbon to hydrogen. Which of these two interactions is our favored interaction? Okay. Well, how did we figure out our favored interaction? We identified the bond. The bond told us how the electrons moved, and then we matched up how those electrons moved to neutralize charges. Okay. Well, the type of bond with carbon to hydrogen is nonpolar covalent, which means what are those electrons doing? Equally shared between the two atoms. Okay? Which means which atom picks up a partial negative? Both. When? At the same time. Meaning neither picks up a charge. So zero charge. Which interaction is the favored interaction? There's no difference. It's 0 to 0. There's no reason for it to interact. Okay? The important part here is that I'm now noticing a difference. The interaction between a nonpolar covalent bond and a nonpolar covalent structure is different than the interaction between a polar covalent bond and a polar covalent bond. If it is now different, what do I then have to do? Point at it and make fun of it, right? No, we have to name it. We have to give it a unique name so that we can then identify it as different from the rest of the world. Okay? Number one, can I call it a bond? No, why not? It's not actually bonded. I like where you're going, but not quite there. A bond means sharing electrons. We're not sharing electrons here. Okay? We're just saying, I just kind of want to hang out near you because you make me less awkward. Okay? That's all that's really happening here. Okay? Not only that, but when I draw a bond, what do I show a bond as? A solid line. And what am I showing these as? Not a solid line. Which means it's, well, not a bond. So I don't want to call it a bond. I want to call it something else. Okay? I'll call it a force. Why? Because pineapple was already taken. Okay? So we now have a force. Well, is the force the same for those two interactions? No. Okay? How are they different? Why is one stronger?
Because that has a partial negative and there's partial positive carbon and the other ones don't have anything.
The whole reason we're interacting is to neutralize the charge. In the polar covalent case, I have this strong partial negative and a strong partial positive. So I want them to interact with each other to neutralize that charge. So that's a strong interaction. In the top case, why interact at all? Okay? So in the bottom case, I'll name that one. Okay? I'll name it based off of what formed it. Okay? So we had this question about dipoles. Polar covalent bonds had dipoles. What is a dipole? Di means two. What is our pole? Negative and positive. Wait, negative and, that was, two. Guess what that is? A dipole. There's a dipole in a polar covalent bond. Okay. So what kind of force would I expect between two molecules that have dipoles? Being the awesomely creative people we are, we call them elephants. Or dipole-dipole forces. Yeah, that was awesomely creative, wasn't it? Okay. We name them directly off of what made them. If we go back and look at the nonpolar situation, okay, we said that's a weaker interaction. There aren't charges to neutralize. Okay. Our initial guess when we looked at that is that was such a weak interaction that it's irrelevant. Okay? That was our first guess. It's so weak I don't care about it. Okay? Which means we don't name it because it's irrelevant. We ignore it. Until some jerk off came along and said, actually, it's kind of important. Okay? And here's how it's important. Here's what it's doing. This is something that we can observe this for. Okay? Well, if the world said it doesn't exist, and then somebody else came in and said, actually it does, and proved the world wrong, the world then goes, yeah, you were actually kind of right. We should give you credit for that. And so that force ends up getting named after the person that discovered it. Or at least the person that got credit for it. And it gets known as a whole smattering of different names. Van der Waals, because a guy by the name of Van der Waals was the one that figured it out. It is also called London dispersion. My guess is as good as yours. I like to say Van der Waals worked in London. It might be true. I don't know. Why not? Okay, London dispersion. The other one that I've also heard, and this one's right up the alley of the other one. Yeah, what? Yeah, I agree. I think that one's a bit annoying, but it's more relevant. Van der Waals doesn't make sense because it's somebody's name. Okay? We should be thinking more along the lines of what the chemistry is, not the person who did it. Okay? London dispersion, London has really nothing to do with anything, but the dispersion actually has something to do with this. What we're looking at is how the electrons are dispersed across the bond. And in the case of the London dispersion, those electrons are dispersed evenly, right? So we don't get a strong attractive force. So we could call it London dispersion because we have an easy dispersion of electrons. Right? The induced dipole. What happens if me being really negative got near somebody else that was really negative? Probably repel away from each other, right? Don't want to be near someone equally negative. Find some opposites attract, right? Okay. If we take that electron cloud, okay, there are still electrons there. They're just being equally shared. But what happens if I bring a whole bunch of electrons up near it? What are all the electrons on that nonpolar molecule going to do? Okay, if we push on your fat on one end, where does the fat go? It moves to the other side. Guess what's happening with the electrons? They're moving to the other side. As the electrons, as a cloud around that molecule shift, what is exposed? What makes that carbon? The what? The protons in the nucleus. So as the electrons shift, what do I start to see get exposed? The nucleus, which happens to be positively charged. The electrons are now overwhelming the other side of the molecule, which means the other side of the molecule becomes negative. And I now have a dipole. But I got that dipole by pushing on it. What happens when I let go? Fat rolls back the other direction. Same thing is going to happen here. The dipole is induced. I have to keep it there. I have to force it to happen. So when we're looking at our London dispersion, now everybody's going to remember fat with London dispersion forces. It's an induced dipole interaction. Okay? Because they both, to have a dipole, must be induced. The word that I tend to associate with that interaction is the London dispersion force, which I write out as LDF. Okay? Because I'm lazy. So, what do we do with all this? Well, we start to compile it all and look at all our interactions. And this ends up coming down to all of our forces. So we'll end up with ionic forces. Where do ionic forces come from? To have an ionic force, I need to have ions. Well, where do I get ions from? What type of bond? An ionic bond. Oh, so if I look at a molecule and find an ionic bond, guess what kind of force it has? An ionic force. Hey, that was really easy. Okay. So our ionic forces are going to come from our ionic bonds. Where did our London dispersion or our van der Waals forces come from? This was our nonpolar covalent bonds. Where did our dipole-dipole force come from? Our polar covalent bonds. So we spent all this time trying to identify our bonds because the bonds allow us to identify our forces. Notice hydrogen bonding is floating in there in the middle. Why? What is hydrogen bonding? It's a force, not a bond. So whoever named that should be taken out back and beaten. Horrible choice of name. Okay. It's a force. How do I generate that force? What kind of bond is going to give me hydrogen bonding? Well, I had three types of bonds. Ionic, covered. Polar covalent, covered. Nonpolar covalent, covered. What type of bond gives me hydrogen bonding? And hydrogen bond does not count as an answer to that question. Okay. First off, what do I expect to see there? Hydrogen. Hydrogen should be present. Okay? So, like carbon to hydrogen. But a carbon to hydrogen bond is nonpolar covalent. And if hydrogen bonding was equivalent to nonpolar covalent, why wouldn't it be written closer to the London dispersion? So there's something else going on there. What was that? So biologists, come on, biology's helped you out here a little bit. I'm actually going to put this as rule 2. We have to have hydrogen. To have hydrogen bonding, you got to have a little bit of fun. Got to have a little fun. Little fun. Fluorine, oxygen, nitrogen. Fluorine, oxygen, and nitrogen must be there. So our rule here is that hydrogen must be bound, actual bond, to fluorine, oxygen, and nitrogen. Okay. Now I have the potential for hydrogen bonding. Okay, so when I look at water, do I have hydrogen? Do I have hydrogen bound to fluorine, oxygen, or nitrogen? Yeah. So do I have hydrogen bonding? Oh. Why not?
I know what it is, but well, because of the partial charge that it's giving off of the oxygen.
Why is there no hydrogen bonding?
Isn't it the two molecules are bonded to each other?
Our forces is the interaction between two molecules. All I have drawn is one molecule. To get hydrogen bonding, I have to have a second molecule. The instant I draw that second molecule, now I can show hydrogen bonding as the attraction between. Okay? Which gets back to rule number 1 for hydrogen bonding. So we could say it has to have two molecules. I think it's a little bit different than that. What type of force do we have in this molecule? Bond, polar covalent, which gets us what kind of dipoles? Thank you for fishing carefully enough. This molecule has a dipole. What does this one have? A dipole. To have hydrogen bonding, what must we have first? A dipole-dipole force. Hydrogen bonding is a dipole-dipole force. This is why it is not shown as a unique force being indented fully to the left. It's indented because it's actually a dipole-dipole force. It just happens to be a stupidly strong dipole-dipole force. It is so strong that we've added its own moniker and called it hydrogen bonding. So rule number 1 is we must have a dipole-dipole. Once I have a dipole-dipole, then I can look for hydrogen being bonded to oxygen, nitrogen, or fluorine. If that is in the case, then I have hydrogen bonding between those molecules. Kind of, sort of? Okay. So now, potentially to the fun part. What the hell do we do with all that? We just labeled the crap out of a bunch of stuff, but what do we do? Okay. What this figure shows, and you won't find this anywhere because it's something I made, is the summary of all interactions. Okay? Intra and inter. Intra and inter meaning inside and outside what? The molecule. So if I pick two atoms that happen to be inside a molecule, well, I'm looking at intramolecular attraction. Intramolecular attractions I call bonds. Okay? If I look at two atoms that are now not part of the same molecule, now I'm looking at intermolecular. If I have an intermolecular attraction, I'm now looking at a force. Why do I have them tied next to each other? Because really all these are is the attractive force, an attraction between any two things. If those two things happen to be in the same compound, we now call it a force. Or sorry, a bond. If they aren't in the same compound, we call it a force. It's a gradient, just like the rainbow. All colors are in this. We have arbitrarily decided and cut the difference between bonds and forces through the ionic bond. Okay? How do we go through and manipulate this? Well, if I have an ionic bond that happens to be coordinated to red color, that's going to mean what force? That's going to be an ionic force that coordinates to, well, the red color. Okay? I have such a large difference in charge in that ionic bond that I end up with an insanely strong attractive force. That force is so strong that it's actually kind of hard to decide, is that a bond or is that a force? Okay? What happens if instead of looking at those two atoms where it's an ionic bond, it's a non-polar covalent bond? Okay? Now the force or the attraction between those two atoms is so insanely strong that I have a black covalent bond. Well, what happens if I take that black covalent bond and I partner it up with another molecule? What kind of attractive force am I going to get there? Well, the nonpolar covalent bond gets me no charges, which means the force I get out of it is very, very small. I would get, say, oh, look at that, a London dispersion force. Okay? Roughly the equivalent on that black scale. So the idea is that we're seeing now a full spectrum between these, and what we're trying to match up is what our bond is, and that then ties to a particular force. Okay? Why, again, do we need this? Okay, well, the bonds, we could look at energies and enthalpies and all sorts of fun stuff that if you move into 151, you have to look at. Okay? And you have to calculate and quantify, and that's awesome and fun. Believe the enthusiasm. Okay? The forces are actually the one that's more important, or at least more interesting to us. Okay? Because I'm now looking at the energy that two particles are now holding to each other. Okay? And I can use that to now predict whether it would be a solid, a liquid, or a gas. If I have a compound that has an ionic bond, that means it'll have an ionic force. Well, is the ionic force strong or weak? It's the strongest force we have. So if I want to now look at the, say, melting point, the temperature at which I transition from a solid to a liquid, I have to break those forces. And for an ionic compound with the strongest force possible, how much energy am I going to have to put in? A lot. So let's think about an ionic compound. I don't know, table salt. What phase is that? It's a solid. Because it has an insanely strong force between those particles. That's holding it together as a solid. To get them to be more mobile like a liquid, I have to put in lots of energy to break that force. Water. What's the deal with water? What kind of bond do we have in water? We had a polar covalent bond, which generated which type of force? Dipole-dipole. And then hydrogen bonding, because I have hydrogen bonded to oxygen. Is hydrogen bonding a stronger or weaker force than ionic? It's a weaker force. So if I'm going to compare water to, say, table salt, I would expect the amount of energy that I need to put into solid water to go to a liquid to be less than for table salt. Is that true? Melting point for salt, 900 degrees Celsius. Melting point for water, 0 degrees Celsius. Was the observation true? Yeah. Methane. Methane is carbon and 4 hydrogens. What type of bond? That is our covalent or our non-polar covalent, which is going to generate which force? London dispersion forces. Are London dispersion forces weak or strong in comparison to hydrogen bonding? Okay. Insanely weak. If we look at methane and the boiling point or the melting point for methane, what is it with respect to water? Much, much, much lower. The forces are now so weak that we can be at like negative degrees Celsius and it's a gas already. Right? To get it to stay a solid, we have to drop to like negative hundreds of degrees Celsius. Right? So we can use our forces to predict what phase we're in. So looking at the structure gets us the forces based off interpretation gets us a phase. Vapor pressure. Well, what was vapor pressure? Might have just had a test on that. Oh, wait, you did. Had to do with evaporation. Okay? The natural amount of our liquid that goes into the gas phase. Okay? For it to go into the gas phase, there has to be something not holding it down as a liquid. What's that thing holding it down as a liquid? It's not the bond. It's the force. And atmospheric pressure contributes, but it's the force between those molecules. So when I look at, say, water with hydrogen bonding versus, say, mercury, mercury is a really weird case. It's got metallic interactions, and that's not even on this list. But we can start to predict something about our vapor pressures based off the forces. What is viscosity? How thick it is. Meaning how much does each individual molecule grab a hold of every other molecule. What happens if our compound has lots of strong intermolecular forces? The viscosity goes up. Okay? Surface tension, solubility, all of these things go back to applying our forces. So if we understand forces, we can predict these things. The big one that comes off of all of this, because you're like, yeah, whatever, those are static things. I don't care about static observations. Last one, reactivity. Reactivity is a sign of what? Chemical or physical change? Chemical change. What was this class? Chemistry. Go figure, if we looked at forces, that allows us to predict something about reactivity. Virtually everything we do in organic chemistry comes back to this chart, electronegativity, and applying that out to our reactivities. It's nuts. Okay? So it is insanely relevant for what we're trying to do in chemistry. Why do we not talk about it as much in lecture? Because it requires us to talk about it. And all of you right now are like, oh God, stop talking, Mike. Okay? You want the calculator, I just want to punch something into the calculator and spit out some number. Okay? It's a thought process behind it. And that's what makes it fascinating. That's what makes it fun. That also makes it very difficult for students to wrap their heads around, because you have to think a hell of a lot more than just punch in a calculator. Okay? So, melting point, boiling point. Which compound has the higher melting point? So we got 4 problems up here. It does say quiz. What do you think? Yeah, we did just have a test. Okay. Fair enough. No. 1, 2, 3, 4. Arguably, 4 is the easiest, and 1 is the hardest. So, of course, when I walk through them with you, I'm going to start with number 4. Melting point and boiling point are going to be dependent on what? The type of force between the molecules. How do I determine the force? By bonds. So I need to be able to look at that structure and say, what are the bonds that are present? What force does that generate? Right? So let's start with 4A. What bonds do you see in 4A? I'm going to say I heard a carbon-hydrogen in there. There's a carbon-oxygen. There's an oxygen-hydrogen. And there's officially an oxygen to carbon. I'm going to need more space than that. Carbon to hydrogen, carbon to carbon. Notice I've gotten the same color. Why would I have them in the same color? They're the same bond, which was nonpolar covalent. Okay. Which then equals what force? A London dispersion force. Okay. I then had the CO bond, which is what type of bond? Polar covalent. Which leads to what type of force? Dipole-dipole, which I'm just going to abbreviate DD. And then lastly, I have the OH bond, which is polar covalent. Which force? We would say dipole-dipole, but then we say hydrogen bonding because we have oxygen bound to hydrogen, which is going to get us our hydrogen bonding. Right? But you're saying, but I don't see the second molecule. When we're looking at our melting point and boiling point, we're giving you a representative structure, and we're now saying you have a container that has that in it. So do you have more than one molecule? Yes, you probably have on the order of 10 to the 23rd molecules. Okay, so slightly more than just 2. Okay. Now we have all of those forces. Which of those forces, and really that was just 4A, which of those forces do I actually care to look at? Why hydrogen bonding? Why am I going to ignore the London dispersion force? Because I agree. I'm going to keep my focus on the strongest intermolecular force, because the strongest intermolecular force is likely to be the one that is going to determine my melting point or boiling point. How about the next compound, 4B? What bonds do we have? Carbon to hydrogen, carbon to carbon, which generates nonpolar covalent, which gets us LDF. Then we have carbon to oxygen, which was polar covalent, which was dipole-dipole. And then we have oxygen to sodium. Sodium? What the heck is that? Oh, sodium's metal, right? Yeah, so that's an ionic bond, which then means an electrostatic or an ionic force. For those of you saying stronger, it's not that you're wrong, but you're jumping ahead. We have an ionic force. Which of those forces am I going to be most concerned about? The ionic force, because it's the strongest one in that set. I'm now going to compare ionic to hydrogen bonding. Which is stronger? Ionic. Which one's going to have the higher melting point? B, because it has the stronger forces. Not the stronger bond. Okay, be careful on that. It actually has the weaker bond, but that generates the stronger force. Okay? So what do you have to do for 3, 2, and 1? The same thing. Go ahead and do 3 and 2. See how far you get with that. I'll write the answers up there. 1, we'll make a quiz. What is today? Thursday. Cool. You have the whole weekend to work on it. So we'll make it a quiz Tuesday. Okay. So it might be a good idea to figure out what's going on with 2 and 3, because maybe you can apply that same rule to 1. And just in case that was not, well, it clearly wasn't obviously stated, 4B has the higher melting point than 4A. So what we're looking at is just comparing the two across. I'll give you those answers. The one with the higher melting point and or boiling point in 3 would be 3B, because hydrogen bonding versus technically dipole-dipole. There's that oxygen in there bound to a carbon. That's a polar covalent, which is dipole-dipole. Hydrogen bonding is still a stronger force than dipole-dipole. So hydrogen bonding, 3B wins. We move up to 2. This one gets a little bit harder. 2A is all London dispersion forces because they're all nonpolar covalent. 2B, we have that oxygen to carbon again, which, as we saw from down there, is dipole-dipole. Which is the stronger force? Dipole-dipole. Which one has the higher melting point?
B.
B. Interesting pattern coming out of that.